Good evening, everybody. I counted 16 primes in this pi product congruence that we want to prove. So not that it's important, as you'll see that it doesn't make any difference how many there are, but just I'm writing this for emphasis because it would probably be somewhere around a 50-digit number that you were trying to determine what it was, reduce modulo 24, or show that it actually reduces to 12 modulo 24. Now, just to be clear on the notation, this is pi product notation. The first prime is the even prime 2, so you have 2 squared, all the rest of the primes are odd, and so you have the product of these squares, and again I think there's 16 of them, not that that's relevant. Okay, notice we use the ellipse to leave out the missing stuff. Okay, now so a couple results here. The very first result that's super important is that assuming p is not equal to 2, p not equal to 2 or 3, and you'll just see, you can tell right off that 2 or 3 doesn't work here. 2 is not congruent to 1 or 5 mod 6, and neither is 3. But you'll notice that 5 is the first one that is. 5 is congruent to 5 mod 6. 7 is congruent to 1 mod 6. What 11 is congruent to what is congruent to 5 mod 6. So the reason why this is true is essentially, I mean, I know this is, P cannot be congruent to 0, right? Mod 6, because that would mean that it wasn't prime, and it couldn't be congruent to 2, 3, or 4. And I hope, I mean, that's clear enough, right? Shouldn't have to prove that. If P were congruent to 0, 2, 3, or 4, that would contradict the primality of P. So P is any prime except for 2 and 3 is congruent to 1 or 5 mod 6. Now you can square congruences just like you can square equalities. So when you square both sides of this, you get P squared is congruent to 1. Notice right here that 25 is congruent to 1 mod 6. Because 25 minus 1 is 24, which is a multiple of 6, right? So notice this is mod 6. We want it to be 24, so what's up? What do we got to do? Well, there's a general truth. There's a general truth that n squared, any integer, not just a prime integer, is congruent to 0 or 1. Mod 4, right? Very famous. That's like one of the first results when you talk about squared integers. Okay, if you think about it, if you just check 0, 1, 2, and 3, they all leave a remainder of 0, 1 mod 4. Now, prime, though, you'd have to rule that out for a prime, right? Because any prime squared could not be congruent, right? And I'll use just the negation here. Could not be congruent to 0 mod 4, because that would mean that 4 would divide the prime number, which is illegal. The prime only has 1 in itself as a divisor, right? So what we get here is we get this result right here, p squared, let me just write it right here, p squared is congruent to 1 mod 4, right? But what does that mean? That means that we know that p squared minus 1 is divisible by 4, and we know that p squared minus 1 is divisible by 6. So that means it has to be, p squared minus 1 has to be divisible by 24. Hope you like that. It's a pretty nice little argument, and it's true for all primes other than the primes 2 and 3. Okay? Now, so back to our problem. So 2 squared times 3 squared is 4 times 9, that's 36. All right, and so we got to write down 36, but then notice all the other squared primes are congruent to 1 modulo 24. So we can write down 1. I'll just do it a few times here, 1, and then we can put our customary ellipsis here. Hopefully that's a prominent ellipsis for you. And then and let me just, I'll write down a few more 1s. But all of these guys here not including 2 squared and 3 squared. See, this part right here would be 36, right? 4 times 9 is 36, right? But the rest of these guys we've just established are equal to 1 modulo 24. So I wrote down 36 and then juxtaposed a bunch of 1s all the way out to 53 squared, right? Okay, but 36 itself is congruent to 12 modulo 24, because when you divide 36 by 24, you get a remainder of 12. Okay, so we have just proved what we set out to prove. Not too exciting once you realize that this is true. It's trivial if once you've established this. This was, quote, the hardest part. The rest of it's easy, right? So anyway, we got a QED going on here, and that's the end of this proof, folks. Thank you.